and we're going to be talking about solving, or actually looking at polymer phase diagrams for this self-healing application. So question 3 on our practice exam. So I'm using polyacrylonitrile, nitrile, PAN. I'm using polypropylene and PVC, polyvinyl chloride. For these new self-healing applications, will blunt crack propagation. Need to figure out what conditions they will mix, if at all. So here's my PVC, PAN, PP. So my polypropylene molecular weight of 62,400. We are assuming a PDI here of 1. Unrealistic, but we're going to stick with it. PAN molecular weight of this. PP has a molecular weight of this. And solubility parameters, found that PVC is this, and this. So what I'm going to start to do immediately is I don't want necessarily the I don't need these molecular weight values. I know that I'm going to eventually have to go to plots of kind of these volume fractions. So I need to kind of look at what is my x sub 1, what is my x sub 2, what is my degree of polymerization of these polymers. And I want to tabulate these values as well. So I'm going to pull up my notebook. So now define everything in this problem that we've kind of been talking about previously. So molecular weight, we want to get at to the degree of polymerization. So we're going to look and define everything in this Mathematica notebook. So I have K, I have my phi 2C, how to calculate that critical value, because that's what we're going to be asked in this problem. My chi 1 2C, my chi equation to solve for the critical temperature from that Hildebrand expression right here. We're going to use an assumption that our monomer volume is 200 angstrom cubed. So we need to convert that to meters cubed. You can see here, we need in order to get our degree of polymerization, we need the repeat unit mass of our PVC, PAN, and polypropylene, which can just be seen right here. To get the degree of polymerization, we take that molecular weight of that polymer divided by the molecular mass to get our degree of polymerization N. So we could see that PVC has a degree of polymerization of 10,000, PAN 100, PP 100. I also included my kind of solvent parameters here. And then now we can go about and solving this problem. Don't want to give away the solution, so we'll get back to that in just a bit. It's with PAN. What is the lowest temperature it could be at in order to ensure mixing? At this temperature, plot a phase diagram with T as the y-axis and this as the x-axis. Label all critical points on the curves. Draw the microstructure within the 2D mix region. So we know that if I'm mixing polypropylene PP with PAN right here, I'm looking at a mixture where my x1 and my x2 are equal. The degree of polymerizations are equal. So I know I'm going to get a curve like this. If I'm sticking with what we usually do, I'm plotting PP. I know my critical point is going to be right here at 0.5. It is going to be symmetric, and it is going to mix low values like this. This is going to be my binodal. My spinodal is going to be right here. I could calculate that. So again, this is the mixed region, this is the demixed region. In here, I'm getting spinodal composition. So in my microstructure, it's like my snakes that kind of go across as they phase separate. Here in that red region, my binodal, I'm going to go through nucleation and growth, so the spheres and the clusters. So how do I calculate kind of these critical parameters? What is my chi C? What is my phi C? Well, I can calculate that right now, again, using these expressions above. So let's calculate phi C. So my phi 2C, which again, I'm plotting this as a function of my phi 2. So in this problem, I'm going to select my 2 species is going to be my PP. My 1 species is going to be my PAN. So I'm then going to do phi 2C. So it is going to be my x1 is going to be my x2 PP, or PAN, excuse me, x2 PAN, and then my x2 PP, what I'm plotting as my x2 is going to be this. So my phi C, 2C, that critical value is that. I could do the same thing now for chi 2C, and that's going to be 1 over 50. So I can plot that, put that on the diagram here, and show that. So that's all those values, plotting this. And if I want to do my phase diagram here as a function of t, it's going to look exactly the same except just flipped. So we're going to find out that critical temperature, but it's the same exact thing. Still, my phi 2C does not remain, it remains unchanged. So it's still kind of focused or centered around there. So plot that. That's it. So plotted those regions, sketch the microstructure, plotted the phase diagram T. We're symmetric, again, because x1 and x2 are equal to one another. So we're centered around that 0.5, that critical parameter we just calculated. What's the lowest temperature I can be at in order to ensure mixing at this temperature? So if I'm at a value of 0.5, which is what we're kind of asked for here, what's the lowest temperature at which you can mix? So that's just going to be correlated to that, the lowest temperature before remixing is going to be this critical temperature, this T sub C. So to calculate T sub C, we know how to do that. That's just using this Hildebrand expression. So I'm going to go back over here, my chi EQ. So plugging in for not V0, V naught. Sorry, plug that in here. So I'm going to get my chi EQ, chi equation, and I'm going to plug in, again, all I need to plug in is for my solubility parameters that I'm mixing. So it doesn't matter which one I do first. So sol a pan, sol pp, and then I'm going to solve for when this is equal to this value here, my critical chi parameter, and solve for temperature. So pretty low temperature. So nice thing again to have in our expression there. So we could deal with that, work with that expression, 2 over 100, and you'll get essentially the solution that you're working with. And let's double check that. I made a little mistake here. Not a little mistake. 20.1. Let's go deal with these. And that's kind of the temperature that we are working with there. So there's a little bit. Let's go ahead and redefine that. Let's redefine everything in this notebook. Work with this. So pretty high temperature. Critical chi and our temperature as a function, we need to get our kind of parameters. So what is our critical phi c? What is our critical chi c? So let's go ahead and solve that in Mathematica. So to get my critical phi c, I just plug in for my pan and pp. It's at a half as we expected, symmetric. For my critical chi c, it's this 2 over 100, 2 divided by 100. If you just look back through the kind of notes for symmetric polymer mixing. So we get this critical chi parameter. And now, if we want to solve for that critical temperature at which everything is going to mix, that lowest temperature, Tc, it's just going to be this. So when my chi equation above here, which we've defined previously, when does that equal this critical chi c? And solve for temperature. So 7 degrees, pretty reasonable. These guys are going to want to kind of mix. So let's go ahead and get to question B. So let me erase, or not erase, but let's get ready to draw some different things. So what happens to this, this phase diagram if I shorten pan? So if I decrease the degree of polymerization of my pan. So now x sub 1 is not equal to x sub 2, and our x sub 2, which is equal to 100, is greater than, let's say the x sub 1 is equal to 5, for example. What's going to happen to the sketch if I shorten pan, decrease the degree of polymerization? So we need to sketch T versus our BPP. Comment on the polymer's ability to mix at this. Well, so can you mix at lower, temperatures than an A? What's your intuition? Blah 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 blah. So let's kind of think about it for a second. Actually, let's kind of plug in for some values. So what will happen to this? So what is going to happen to my critical feed value? So I know that my x2 pan and my x2 pp, they're both 100. So just like what I said previously, so we are going to shorten pan. So if I shorten my pan to, let's say, 5, what is this value? How is it going to change? It's shifting to the left, right? To lower values of my phi pp, my x2. So my critical value is shifting, further and further kind of to the left there. So let's also kind of see what happens to our chi 1, 2c if I do 5 and 100 x2 pp. Let me get a new. So you can see that this value, what's happening to here? So previously, pi 1, 2c for x2 or x2 pan, x2 pp, numerically, really low, right? So I needed high temperatures in order to kind of deal with this one. So let's look at what's going to happen here for kind of this expression. So what's happening? So schematically, we can see here, actually, here, let me draw it here. If I'm doing a chi, you can't draw it at the same time. If I'm drawing a chi sketch, previously we had a picture like this. So we had phi pp. So it was very, very, very low, that critical chi, and it was symmetric. But now it's shifting over here, and what's happening to my critical chi value? So this was my previous one, so this was like 0.02. That's like 0.14. So it's raising the critical chi, and it's shifting to the kind of left here. So the same thing would be happening over here. Same critical chi value is shifting to the left, and our temperature is going to be decreasing. So it's going to be asymmetric too. Again, I'm trying to draw that poorly, but that's kind of the critical thing. Our chi value is increasing. That means that our temperature is going to be at a lower value than previously. So low chi value means, again, chi proportional to 1 over T. So if chi is low, that means I need a high temperature to mix. So previously, the graph would look like this. Symmetric, much higher temperatures. That's essentially what we're kind of playing with here. And actually, you could kind of, again, it doesn't specify, but you could kind of prove that and solve for, let's go ahead and look at this. Oops, excuse me. So if we're dealing with pan pp, solubility, and we change it like we just did here, we can kind of see this temperature change lowers. Exactly. So that's what's happening. So comment on the ability of the polymers to mix at 5 pp. Now it's a little bit difficult because again, you would expect it. Again, it's going to be easier to mix, right? So I can mix at higher and higher chi values because this is shifting up. So that would be kind of your intuition. But to solve this mathematically, what would we need? Well, we're no longer symmetric, so we can only plot the spinodal, but it's really the binodal that kind of tells you that outer layer where we mix. So you want to be careful. To solve this explicitly, we need to kind of, again, mathematically at every point, take that binodal, figure out the common tangents, and then draw that to kind of see if we could really solve this solution mathematically fully. But I'd be pretty confident saying that it's going to be easier to mix, just kind of what we drew out here. Excellent. So what's my critical chi and phi value if I mix PP, PVC? What about pan and PVC? All right, so let's just, right now we're just going through calculations. So critical chi, so let's go ahead. I'm going to grab all these expressions so we can knock them out all at once. So I need my critical phi c. If I mix, I need to mix PP, or my x2 PP, x2 PVC. So I want that. That's my critical. If I want my critical chi, x2 PP, x2 PVC, right here. And then I could just plug in my x2 pp, x2 pvc, my solubility pp, my solubility pvc. There it is, right there. And I could do the same thing for Control C. Now I'm mixing pan and pvc. And x2 pan. Same thing, because they're symmetric, as you might expect. Easy answer there. So, finally, undergraduates, behind my back, ran an experiment to calculate the free energy of mixing for 2 mystery materials. Several of the free energy curves can be seen below. Plot the resultant phase diagram. Again, T versus V2. What can we be mixing here? Also rank each curve in terms of lowest to highest chi value. So, let's go ahead and look at these free energy curves. So I always want to plot chi versus my phi2 first. So looking at these curves, here we are fully mixing all the time. We're fully concave up, no points of inflection. So my chi here is the lowest, really, really, really low. Not for less than 0, but chi is low, very, very low, because everything's mixing, right? Low chi inversely proportional to temperature. High temperature, things want to mix. So that's my lowest chi value. I can kind of put this back. I'm going to draw this actually. This is my kind of color for this one. And then I'm going to have, this is my color for this one. I'm going to have this my color here. I'm going to have this as my color here. So that's my chi there. So let's look at what else is happening here. So let me get here. I have a common tangent right here and here. So between these values of like 0.8 and the 0.1, I'm demixed in here. Again, I'm on this is my free energy curve for mixing. I want to drop down if I'm at any of these compositions. So I'm demixed in these regions right here. So that's that 0.1 region, and then so it's a pretty large, pretty decently large region. But as we're going to see here in a second, if I look at my orange, in my orange line here, I have a common tangent between right here and right here. So it's like getting into like 0.9 range. So that's even a larger region demixed. And then finally, in the purple region here, it's almost at 0, and here we're at like 0.95. So basically, almost everything is demixed. So nothing likes to demix. So this is going to be my highest chi parameter. So it's going to occur at a chi like around right here. And this is going to be my next lowest. Actually, my orange could be like right here. And then my purple, actually my green, excuse me, is going to be right here. And I kind of know those values of like, so like this one was at, we said like 0.1, let's say like 0.8. So that's where those binodal points occurred. And then we saw it kind of widen out. So it got a little bit wider here. And got a little bit wider here. And then it's really shifting actually disproportionately, which I'm trying to kind of show, where it's like almost at 0 here. It's going to be tough to draw at 0, but anyways, you get the picture here. So we're still not. So the curve in the end is going to look something like this. And it's going to be a little bit kind of disproportionately shifted like this. So why is it shifted? Well, we know that these, basically, these free energy curves, the common tangents are not equal to 0, that slope. So we know that for this material, x1 not equal x2. So we could be dealing with a polymer solvent mixture, a solvent-solvent mixture, et cetera, et cetera, et cetera. We don't know because, again, we don't know necessarily because we need to kind of have like the resultant phase diagram to see the critical chi value. So if we had the chi 1c or the critical chi c, then we'd be able to solve this problem, fully. However, we do not have that at our disposal. So we know it's asymmetric, so it could be polymer. It could be a polymer-polymer mixture where x1 and x2 are not equal to 0, or it could be a polymer-solvent mixture. But we know, again, you can kind of see that this curve, it's like a little bit shifting, looks a little bit asymmetric towards the left. But again, that's what we definitely know it's asymmetric. And yeah, that's essentially what we are working with here. So yeah, that's pretty much all we think. Let's look back and make sure we solved the full problem. This is a hard one. Phase diagram. Okay, and then to flip it, what could we be mixing here? Ranking curve. Exactly, that's how we want to approach this problem. So to get the T, again, all we do is flip. So 2, we would just flip it like this. That's it. So again, shifted, to the left there, approximately. But yeah, that's all we've got here. So I hope you've enjoyed that description, enjoyed that lecture. So next time we're going to get into the last problem, and we're going to be solving for this last problem in our exam with osmotic pressure, membrane osmometry. So I'll see you all next time. Thanks. Bye.